Hi, Professor. I'm Luis Alfredo, and this is my video trying to explain how I did my argumentative exam exercises, the ones that I was able to perform in the time we had. Starting with the argumentative, for the situation one of our argumentative exam, we have it divided in two parts. The part A being a straight film using Biot-Savart law, so here's all the explanation. At the beginning, we have the equation for the magnetic field in one dimension without having a test point along any point of the wire with its own current. But if we want to know what's the magnetic field of at a certain point in space, we should need to tune out this equation. So supposing we're on a 3D field and the wire is on the Z axis, then we have to draw the the differential of line in the direction of current as always. That's like a rule. And so the distance that it's going to be between the test point and some point of the wire is going to be the separation vector. What's the separation vector? Is just a subtraction between two vectors that mark between the vectors on the end and the beginning of this separation vector. Then to do the vectors calculation, we move to cylindrical coordinates because magnetic fields always move in round shapes along their source, in this case, the wire along the z-axis, and it's easier to do the calculations. Then by analyzing the diagram, we can see that the differential of line is also along the z-axis. So this vector's magnitude and direction is going to be equal to the z along z. We can also see that all these vectors form a triangular shape, and we need the value, and to calculate the value R, so we can apply the Pythagoras theorem, that it's the one it's shown over there in blue. Then we apply the formula of the magnetic field, and it's just going to be the differential of line. We are just replacing values. Then we're carrying out the cross product, having the value of our cross product between the differential of line and the separation vector. And as we can observe in this integral, the cross product between these two vectors is the only thing among the integral that tells us the direction of the magnitude of the magnetic field. And comparing it to the cylindrical coordinate system in always or completely makes sense because it's telling us that it goes from a certain distance on Z, where the wire is, over rho, that is the distance from the wire to the observation point, and all along the phi or the phi direction, if I'm not wrong. I don't remember pretty good the name of the shape. Then we just have this integral when we already replace the dot product and the magnitude of the vector r, that is the one down here in the integral. And finally, to simplify our integral, we just trigonometric substitution to get an easier result. In this case, we're going to be using the cotangent of the angle, being the angle, the one over here. We do the substitution, and then we just apply some algebra knowledge to finally get this equation in red. Then we go to the part two, that is a magnetic field from a square from a square current loop at point 0, 0, Z0. So I first planted it with Ampere's law, but I ended up doing it with Biot-Savart because I noticed that you tell us that we should use Biot-Savart law to no, I think I did. No, yes, I do. I use Biot-Savart law because I thought that we were supposed to use Biot-Savart, but at the beginning, my idea was to use Ampere's law. So this is not correct. We can see here that the current is going clockwise, and from the analysis made in class, from the law of cosines, we get this equation that is the one that we have over here, and we will have to apply all this process to each one of the segments of the square loop to get the magnetic field from the observation point to each one of these segments, and thinking of them as if it were like just different wires, not if they were a complete full shape. So first, we calculate A, B, and C for this triangle. So it's basically just applying Pythagoras theorem to each one of them and replacing correctly the values of x, y, and z for the points A, B, and C, being A, B, or B, depending on what we want, A, B, or C. And then we just get the magnitudes or the values. In this case, A is always going to be equal to A because it's always going to be, maybe just in the way that I did the problem, it's always going to be A because that's how I planted all the triangles. In this case, we can see that also B is equal to 0, and well, this is all the calculations that we do for each one of the triangles. Then we perform out the cross product that is going to tell us the direction of the current. And then if we compare it with the right hand rule, we can confirm the direction is correct. And then we go to perform the integral. Here we have that rho equals to z0. So rho equals z0. That is how we can see over here at the diagram. There we go. Then it's just replacing the values, making some algebra, and finally arriving into this formula. Then we do the same for segment 2, draw our triangle, put our values, our lines, determine which one of them is which, then get the values of A. As I already told you, A is always going to be A. The values of B and C are going to be changing a bit, but they also repeat because of the way I planned out the triangles. Then carry out the cross product. This is the second result. For the third segment, we do exactly the same. A, B, C, the triangles, their values, then replacing on the formula already integrated and arriving to the final result. And then we got the fourth and last segment. Again, the exact same process, and we get until here. So we can observe that segment 1 and 3 have the same magnitude but in different direction, as it happens with the other two segments, the segment 2 and segment 4. And this makes total sense because analyzing it, they really are technically the same. They just are in different position and they have a different direction. So finally, this will be our final formula. That is the total magnetic field of all the magnetic fields summed up. So I did it like this. So the H total final is going to be the H total 1, that it's the first magnetic field plus the second magnetic field, plus the H total 2, that is the third magnetic field plus the fourth magnetic field, and we get that. Then going on to our second situation, it's at the magnetic field due to a circular loop in the x plane. So the position vector R is how we show it in green. There we have the diagram, and it's going to be the same for every point on the circular loop because its center is located at the origin. And we have two observation points, that it's the point 1 and point 2, that they are exactly the same, just in different sides of the axis, in positive and the negative, but they have the same distance. So as we know, R is a separation vector, then we calculate it, carry out the cross product, but we know that the loop center is at the origin, so our resultant components of the vector cancel out because they all have an opposite of the same magnitude, but in opposite direction. So now the integral ends up and ends up being like this. Because of the differential, we know that we should integrate phi or theta. We perform out and carry out the integral, and for minus this, and this is the final result. But for the integral with respect to the observation point, that it's in the positive y-axis, that is y0. In the case of the point observation point that is in the negative y0, it would be exactly the same process, but the only difference it would be that the um, the current it will be going in anti-clockwise sense with respect to that observation point. So our result, our final equation, would be positive instead of negative. Going on to the third problem, that is situation 3, magnetic field due to an infinite current sheet. So we have here diagram. We have then the diagram so from the Z side, like from the point of view of the Z axis. And we have two sides that are parallel to X axis. And these two have a contribution to the integral because the magnetic field following the right hand rule is going to be around parallel, is going to be around or parallel to the y-axis. And because the sheet is infinite and on the yc plane by symmetry, the magnetic field has equal magnitude to x or minus x, just with different direction, and it's also uniform over y. And because of the definition of the sheet stated at the beginning, and because the current is flowing along minus z. Now to integrate it, we have to divide it into four integrals because we have, again, four different lines, four different segments in the ones that the magnetic field is flowing or going, and also the current. So as we already said, segments 4 to 1, that it's the upper one, and 2 to 3, that is the lower one, do not contribute because they are parallel and also because they are the infinite sides of the sheets. So we are just going to carry out the process for segment 1 and 2 and segment 3 and 4, in which we have the procedure over here. Then we use the current density to obtain this final formula. And so the direction at x equal to 0, well, at x0, it's that equation over there. As for minus x0, it's the same, but in the other way, so in negative y direction, also according to the right-hand rule. And so what it is that magnetic field goes from x0 to minus x0, and this shows discontinuity for the magnetic field along the sheet. But if we want to obtain the constant magnetic field, we can simply like subtract them, and we would obtain just the permittivity of free space times K, that is the density of current expression that denotes a constant magnetic field all over the sheet, and one which has, compared to a solenoid, as said before, constant magnetic field in both sides, not like the solenoid in which has magnetic fields varies with the distance. Now, following up with situation number 4, we have motion of a charged particle in a magnetic field. So this is our little diagram, the initial conditions, and we need to apply the Lorentz force. That is that equation over there. We set up first the Newton's second law, carry out the process for the velocity vector. Then we substitute it on the formula and carry out again the cross product. Our cross product, we substitute it in the formula, and then we start the matchup of the system of equations. Then we are going to start solving the system of equations. And here, what we do is apply a second differential, a second derivative on both sides. So we can have a term with derivative on the right side of the equation. So now we can start to do the substitution and start again the process of solving the system of on differential equations. And then here we have the result that it says that we have an ordinary differential equation that it's linear with constant coefficients and homogeneous and with second order. So using the tables, the solution for that equation is as follows. Then we apply the formula down here. So we get the value of the velocity along z, and then the velocity, we substitute these values onto the ones that we had before. So now to know what is A, B, and C, we're going to use the initial conditions that we're going to apply on each one of the components of the velocity, being on X or on Y or in Z, with their respective initial condition, the X initial condition, Y initial condition, or Z initial condition. And we go back again to the beginning that it with the same initial conditions as we had in the beginning. So we're going to perform the integral with these initial conditions, and we have that the component in X is going to be 0, in Y is going to be minus V0, and in Z is going to be 0. So we get that the force is going to be equal to 0 in the first method. Then we're going to try out another method that is going to be the force equals the mass times the acceleration. So again, we know that we're going to start first with the cross product between the vector of the velocity and the vector of the magnetic field. And in here, we are also getting that the force is equal to 0. So we can deduce that the force is going into the other direction or into the opposite direction, canceling out itself and turning into 0. That's why we have force equal to 0 and velocity as a constant. That's why also why we don't have any acceleration. So the particle it's not experiencing any force or acceleration, and it has a URM, a uniformly rectilinear movement that also matches up with the trajectory being just over the y-axis and in the positive direction, and the other one in negative, that is going to be the force. And so it has no periodicity as it has no other components, no x components or no z components. It goes just over the y-axis, and it also has no variations. So it has no circular or helix motion because, as we said, it stays on the same plane. And finally, we come to the last exercise that I could perform, that I had time to perform. That is the situation number 5. It's magnetic force on the current carrying loop due to a long straight wire. So first, the magnetic field by an infinite wire on any point on the space. We have that formula that we already derived in the first exercise. But in this case, because the wire is infinite and located on the z-axis, we can say that with respect to any point in space, it's making a 180 degrees angle because it goes all along over z in positive and in negative. So there's going to be a point that the distance between the wire and the observation point, it's going to be so minimal that the angles are going to almost reach 180 and 0. So these angles are the ones that we're going to substitute into our formula, being alpha 2 0 and alpha 1 pi. Instead of using 180, we're using it in polar coordinate systems. So we know that pi is the one that goes 0 to pi. It's the amount of movement that you have around the plane in cylindrical coordinates from going to one side to another of the same plane or the same axis. I don't know if I explained myself very well. Leading us to this final result of the magnetic field or the magnetic force. And then we have to determine this magnetic force at each one of the segments of a rectangular loop. I erased there's the loop. So we're going to start with the segment number 1, that is going to be this from 1 to 2. There it says. So we are going to use the differential line in opposite direction to have it. Okay, this is taking into account that the current of the infinite wire is going into positive set, and the current of the rectangular loop is going into um, counter counterclockwise direction. So here we're going to use the differential of line in opposite direction to have it positive, and we'll give the weight of the direction and the signs to the integration limits. So we have then this formula. We started just by, then we started to just do substitutions and multiplications. So this integral says that the wires are going to still attract themselves, we but we'll solve this with the correct use of the integration limits. This is integration until here. They will attract if the current were going in the same direction, but we have it in opposite directions. So that's what we're going to rearrange over here with the integration limits that are going to give us the final equation positive. So it tells us that the current is going in the opposite direction of the current of the infinite wire. We could have also solved it with the differential of line, have it negative, but I prefer to use it with the integration limits in the other way around to have it negative. We perform it, then we perform again the same process in the segment 2 to 3. This is the only one. The first one is the only one in which we do this different step, because it's the only one that has an opposite current. All the other ones have it parallel and going outside of the first current or inside, or well, towards the first current of the infinite wire. Again, we carry out the same process, do the substitutions, put our limits, then we derive the second equation for the segment number 2. Then for segment number 3 or 4, we have both currents going into the same direction, so it's negative. There is that will be the place where they attract the both wires, if they were wires. And then for the segment number 4, we exactly do the same as we did in the other ones. And finally, we got this equation. We here at the end just do this little change. At the beginning, we had the natural logarithm of rho 0 minus the natural logarithm of rho 0 plus w, but we interchange them and we add a negative sign at the beginning, so we could perform this property of the logarithms, and it would also be negative as it should be. So this change that we did, it doesn't has any weight on the signs of the equation. It's just like a rearrangement of the same equation, so we can have it in a more compact or simpler way. And so that would be all the exercises that I had time to perform for my argumentative exam. Thank you so